Thanks, Mike. It's nice to be introduced by Mike, but I've got to keep in mind that Mike's published a hell of a lot of papers on current fire occurrence, and he has also done his PhD on it, so a little bit intimidating, but it was good to have him involved in some of this work that I'm presenting today to kick-start it along and get it moving a lot faster than it would have otherwise. So firstly, I'll just talk about what do I mean by fire occurrence, and I guess there's a number of different ways of interpreting it, but here I'm talking about the when and where of fire outbreaks. When are they likely to occur? Whereabouts are they more likely to occur? Is a given day more likely to have any fires or some fires? If so, how many? A lot of them, or just a few? What parts of the landscape are most prone to ignition? And does this vary for different fire causes? So they're some of the issues that fire occurrence statistics have been used for, and I guess when I'm talking about fire occurrence statistics, I'm talking about the data sets that agencies have on their fire incidents, and they're a real rich resource for doing all sorts of things, as I'll go into a little bit further. And there has been quite a bit of research done on this topic, particularly in the last few years as the data sets have become more available, and as the as computing powers allowed better analysis of that sort of data. And a lot of this work's been done particularly in North America and Europe. And they've been done as regional case studies using certain agencies' data sets based in particular climate zones or vegetation types. And most of the research that has been published recently has been looking into spatial patterns of fire occurrence. I'm only going to briefly touch on this, but this work has again largely been done in Europe and North America, and it's come up with some fairly consistent findings in that human-caused ignitions are most likely to occur near where humans are, particularly in areas that are close to roads and access points, even railways, and particularly around homes, towns and suburbs and that sort of thing. So kind of more or less what you'd expect. With us, and there's also seems to be a fair bit of a socio-economic influence there as well. Lightning ignitions, which you'll hear about a lot in the next talk, they're more likely generally in elevated areas. And this work, as I mentioned, has been done mostly in the Northern Hemisphere. There's only one recent study that's been done in Australia by Trent Penman and colleagues from the University of Wollongong, and they've found that using data from the Sydney region, that the findings there are more or less consistent and hold true as well. That's about all I'm going to talk about with the spatial side of it, but most of the work I've done here has been looking at the temporal patterns, and here I'm using a case study from southwest corner of Western Australia, using data from DFAS, formerly known as FISA, up to about a year ago, and DPAW, or Department of Parks and Wildlife, which were recently known as DEC. This work here is part of the Bushfire CRC project that I've been working on for a couple of years now, and acknowledge their funding here. Firstly, there's sort of two sub-studies that I'm going to present here. One looking at fire timing for different ignition causes, and the others sort of looking into predicting the daily number of fires within defined management areas, so that the management areas that agencies use for organising their own resources. So firstly, looking into fire timing. Here, I guess the main aim here is to look at ignitions from different causes, how they vary in timing, and also including how they vary with weather. Which fire causes have, and I'm interested in looking at what fire causes have unusual time profiles. And this case study is using the area around Perth, and it's only using data from from DFAS, the Department of Fire and Emergency Services. I keep calling them FISA. And the reason for that is that they're responsible for most of the fires in this area. And they've got a data set that's based on the air system, the Australian I can't remember the acronym. It was Australian Incident Reporting System, I think, and it has, you know, tens or probably nearly 100 different fire causes, and I've whittled them down to 17. I'm considering this area, which includes sort of urban and peri-urban areas around Perth. But the 17 causes are here. I'm not going to go through them all, but they broadly fit into sort of natural ignition causes, which are mainly lightning, some deliberate. There's a fair array of different accidental ignition causes, and also a few different categories that are undetermined. Here, this data set I'm looking at is for 8 years of data between the 2004 and 2005 season to the 11-12 season, and I'm comparing it with met observations from Perth Airport as well. And you can see in this data set here that most of the ignitions, or just 55% there, are deliberate, so arson or suspected arson. And as I mentioned, there's 31,000 plus fires. So looking into the fire occurrence patterns in terms of month, here it's got this is for all fires in the data set, and on the y-axis here you can see I'm looking at proportions. So this is a sort of proportional analysis comparing what proportions of fires occurred in which month, and how that varies across the year. The months, this sort of fits the typical pattern that you expect in terms of fuel's more available in summer, there are more fires in summer, and so it matches FDI there quite well, and it also matches the fuel moisture content in the opposite sort of way, in an inverse kind of way, because the fuel's more available in the summer. So that's pretty much what you'd expect. So if I break this down into the different ignition cause categories, here the grey lines showing the proportions for all causes. The black lines are showing the profiles for the different ignition causes, and the red ones are those profiles for the different ignition causes that are statistically significant in terms of being different from the average, or for all fire causes here. So here there are the four of the ones that are different here are a little bit more exaggerated than what you'd expect for all causes, and that sort of shows that they're more prone to occurring in summer than average, and less prone so in the wetter winter months. And I should have mentioned that this part of the world, of course, has a Mediterranean climate, so that the summers are hot and dry, the winters are cool and wet. So it's a little bit more pronounced than say other places in terms of the summer and winter differential. So these different causes here have they're more sensitive to season than the other causes. Interestingly here, burn-offs, or these are escapes from prescribed burns, but either private or public, but most of them are private. You can see this profile is quite different, and the peaks there are within in the main burning season. So sort of as you'd expect, there's a high probability of losing a prescribed burn when there's more prescribed burns going on. Looking at the profile in terms of day, day of the week, here we've got Sunday, Monday through to Sunday through to Saturday along the x-axis there, and you can see there's peaks on the weekend. And so in general, fires are more likely to occur on weekends a little bit. And as you'd expect, the weather's fairly flat then, although over the 8 years it seems that Thursdays are slightly wetter and Sundays are slightly drier, but there's not much in it. But it certainly doesn't correlate with the profile for the fire occurrence there. So if I look at this across the different ignition causes, you can see that lightning has quite a different profile, and this is really a result of having lightning fires on only a few days, but when you're having lightning, you're having lots of lightning on those few days, and again we'll hear about that a lot more next. The suspicious fires of known cause, they have stronger peaks on the weekend than average, and it's only slight, but this is a result of the different sample sizes and for the different causes. Ignitions from cigarettes and smoking are more or less constant across the week. There's not much variation there. Cutting and welding and vehicles, variation there is mainly due to the low sample number. Fireworks and explosives is an interesting one. Seems to peak on Saturday nights and Friday nights, and as you'll see in the later slides, it does peak on New Year's Eve, and there's particularly one New Year's Eve that happened to coincide with a Saturday night, and particularly high fire danger, and so that particular one day within the 8 years picked up a lot of the fireworks ignitions. I think they might have. I'm not sure, but I think they might have tightened up their regulations after that particular year as well. This graph here is showing how the proportion of fires varies with hour of the day, and the peak in the mid-afternoon there is more or less what you'd expect in terms of weather. The green line here is FDI, and the blue one's fuel moisture content. The difference there with weather is it appears that the ignitions are slightly delayed, and there's a lot more ignitions overnight than you might expect just based on the weather alone. But more or less, it's following that fuel availability. Looking at that in terms of the different ignition causes, there are a few that stand out, and in particular the cigarettes and smoking materials and cutting and welding materials there have got much more pronounced peak than the other ignition causes. Fireworks seem to have that early morning peak, so just after midnight, and that tends to coincide with a few major events, but yeah, mainly due to early morning New Year's Day. I think there's also a few Australia Days that are up there as well. The rekindled fires seem to occur a little bit earlier in the day, so they're a little bit more aligned with the fire danger than the other causes. And these rekindled fires are they're reignitions from wildfires that have been thought to have been fully contained and extinguished, but that have popped up again, as they occasionally do. This graph here is looking at it in terms of FDI. So the x-axis here is an FDI decile. They're split up in deciles to get them into even-sized groups. Otherwise, you'd end up with lots of time within the low FDIs and few times within the higher FDIs. Here I'm. I don't know if you can see that there's some dashed lines. They correspond to the different fire danger classes, but as you'd expect, the average fire causes are more likely to occur when FDI is high, and the FDI calculated here is to the nearest hour of the ignition, and the proportions are based on that. So the ones that stick out here are again, cigarettes and smoking, cutting and welding, the rekindled fires as previously shown. So interesting from particularly the first two, the cigarettes and the cutting and welding. These are small heat ignition sources. So if you think of a spark from a cutter or welder, it's quite small. It doesn't have much residual time. Same with the cigarette butt. Cigarette ignition has a very low probability of actually starting a fire. There's probably a bit of noise within this data in that I really don't expect that there would really be much ignition from these, from particularly cigarettes at lower fire danger indices, because it's a really low probability to get a cigarette butt to take light. But the problem is that there are so many cigarette butts out there that probability is more likely just because of the sheer number of them that are out there or getting dropped out there. This is, I'll move on to the next study, and this is predicting the number of daily fires, and this work's also involved Lockie and Mike and Jim Gould as part of it, and the aim of this work was to develop and evaluate some models that predict the number of human-caused fires within the operational management areas that are used by the Western Australian agencies. So they've got certain management areas that they use. Here we're only considering the non-urban areas because I sort of really wanted to focus in on the bushfire aspect, so not the fires that might be just burning a median strip or that. There are 10 management areas. I'm only considering human-caused fires. I couldn't get enough causational information about the lightning ignitions because the company that does that wants to charge an arm and a leg for the data. And here I'm using one weather station within each of the management areas and comparing the observations there. So here we're developing models that are based on 3 years of data for each management zone and considering the fires that have been attended by each of the agencies within those. I know I'm using a subsequent year of data for validating those models. And the models are based on a negative binomial regression, which is similar to Poisson modelling, which is what historically most of this sort of modelling's been done. I won't go into it, but it's a little bit better at coping with some variability within the data than the Poisson version. I've applied a single model form, so a form that uses the same input variables for all of the different management areas, and the aim here is to I've also considered looking at the range of fires that might occur in a day, so I can say that you might expect between 2 and 8 fires in a day rather than say, please expect 5 fires tomorrow. There's quite a bit of noise in this data, as you'll see soon. So I tested quite a few different variables, but through the sort of stepwise process, I've come up with minimum daily fuel moisture content, the number of human-caused bushfires that have occurred in the previous 2 weeks, whether a day is a work day or not, so Monday to Friday, but not a public holiday, and also the recent rainfall. Here's a result of a model, and it looks a bit noisy here, but this is the model predictions applied to the test year, or the year that's the year of data that's being used to sort of validate the model. The black line's the actual model prediction. The blue area are the confidence intervals sort of used to predict the daily range, and the green dots correspond to days where the number's been correctly predicted, so about 86% in this case, and this case is from the area with the most number of fires, and the triangles represent where it's under-predicted and over-predicted, and in particular the days that are under-predicted are a bit of concern. These are the peak days that you want to pick up, and so it's a bit disappointing to miss those. But in reality, it's a result of the whole regression process in that you've got a lot of days with similar conditions but different fire counts, and there's still a fair degree of randomness in the data, which is sort of unable to be picked up. And try as I have for quite a while, and shed a bit of sweat over this one, but it couldn't sort of really be brought in any better than that, unfortunately. Similar result for an area with sort of middle amount of fire activity, and that there's a bit better in the prediction statistics look a little bit better, but there's less day-to-day variation here, and even more so with the area with the lowest amount of fire activity, and this is along the south coast to the west of Albany, this particular area. But there's very few days with fires, and so while the prediction statistics look good, it's not really appropriate to apply here, and so I considered whether it's better to consider the probability of a fire day, so whether a day has one or more fires or not. And so this sort of analysis looks into a logistic regression, and you're working out whether a day will or not have any more, have one or more fires. And the results still a bit mixed because the low frequency of fires, and they're occurring on days that are very similar to other days that have no fires at all. So this method's probably not, or this type of model can't probably be developed for areas with really low fire counts or low fire activity. Probably a little bit quick, aren't I? The number, I'll summarise the stuff here, but I guess one of the main points that I really want to take is that the fire incident data is really valuable. We've been collecting it for years, and it's been getting better over the years, and particularly in the last few years. But just as I think Jeff Keppert spoke about the value of weather records over in his presentation yesterday, fire incident records are of similar value for our industry, and that they'll help us understand the temporal and spatial variations in ignition patterns, and in a wider context in just general fire occurrence. We can do a lot more with them, and they can be used to make predictive tools that will again go back into the industry and help with operational planning and things like that. So there's a lot of value in there, and I guess I couldn't stress enough the importance for fire agencies to maintain and ensure that their fire incident data is of really good high quality. So with the results I've showed here, the timing of ignition sort of generally follows the fire danger and fuel moisture availability that you'd expect. All causes are more frequently when the fire danger is higher and the fuel moisture content is low, and fuels are more available for burning. Some causes are a lot more sensitive to that than others, and that's particularly those with small heat outputs. Timing is also affected by human activity, particularly day of the week. I didn't mention it before, but public holidays and school holidays also have much higher fire occurrence than sort of days where kids are at school or behaving themselves or whatever. There's that aspect as well. Predicting the daily number of fires is difficult. It can be done to some sort of level, but it can produce a tool that's of some information, some help to help with daily planning operations, but it's not the be-all and end-all. But hopefully, what we've done here is of some use to fire managers. I'll leave it there. I think I've got a fair bit of time for questions.